Okay, thank you very much for giving the opportunity of presenting WILLOW project. I'm Ainhoa Cortés. I work at CEIT, which is a research institute in the Basque country in the north of Spain. And yeah, I'm going to present the WILLOW project, which is a project funded by the European Union. Okay, some general data of the project. As Tuhfe said, this project was granted in the topic integrated wind farm control. And yeah, the acronym is WILLOW, and the granted was around 5.8 million of euros. The project started yeah, recently in October this year, and will finish in 2026 in September. So this is the consortium of the WILLOW project. We are 12 partners from 5 countries. We have 4 research institutes, CEIT from Spain, which are we are the coordinators, Flanders Make from Belgium, Sintef Energy Research from Norway, and Series from Belgium. Then we have a university, VUB from Belgium, one offshore operator, which is Northern, and 5 SMEs, Alarion from Spain, CQ from the Netherlands, TSI also from Spain, 2-4C from Belgium, and Wolfel from Germany. And last but not least, one cluster, which is the Basque Energy Cluster from Spain. Then this is how this presentation is organized. First, I will give you the context and the challenges of this project. Then I will present the objectives. Next, the work packages and activities. Then the outcomes of WILLOW and the expected impacts of the project. Then let me put in context the motivation of these projects. Nowadays, the operation of offshore wind farms is not ideal. We must handle with some issues like the fluctuation of wind availability and power grid demand. In addition, in offshore, we have harsh environmental conditions affecting negatively the structural health of wind turbines. On the other hand, wind farms should deliver commanded output power instead of the maximum to follow the needs of the grid operator. And this implies down-regulation of the wind farm to produce less power than available. Then today, different strategies are applied, like stopping a few turbines and letting others producing maximum power, or regulating each turbine by the same amount of power. And these kind of strategies affect negatively the effective life of the structure. And this what in WILLOW we want to avoid. Okay. Then there is a lack of success in implementing new decision-making schemes. In fact, in offshore, we must consider component degradation, and it's difficult or really complex to handle together component degradation and grid integration. Additionally, in offshore, we have higher degradation rates, such as corrosion due to moisture and salinity, and additional loads due to waves, tides, and currents. Okay. Then, aligned with all of this, we'll propose 3 main objectives. The first one is to design a global structural health monitoring system based on loads, accelerations, images, thickness losses, different kind of parameters, and considering problems like fatigue, pitting corrosion, and coating degradation. The idea is to develop physical and virtual sensors combined with machine learning techniques. The second objective is more focused on the design of prognostic tools by combining SCADA and structural health monitoring data, and by using physical models and machine learning methods to predict the consumed lifetime and the remaining useful life of the critical structures. And the third objective is to design decision-making support tools for smart power dispatch in curtailed conditions and to optimize the operational maintenance scheduling as well. Then this picture shows the four technical work packages we have in WILLOW. The first one is focused on the definition of the use cases, the system requirements, the cybersecurity strategy for this solution, the environmental impact. Then right now we are working mainly on this work package, defining the use cases we want to handle. This work package is led by the offshore operator, with Northern. Then we have the work package 2 more focused on the design of the novel structural health monitoring solution led by CEIT. And here we want to combine structural health monitoring techniques like based on ultrasounds, spectroscopy, electrochemical sensors, accelerometers, string gauges, virtual sensing, different technologies combined with drone-based inspections. And the aim is to handle problems like pitting corrosion and coating degradation and load damages and analyze the interaction between these problems. Then this work package will work at wind turbine and component level and will provide data to work package 3 and 4, which will work at wind farm level. Work package 3 will work on the design of data-driven prognosis tools, corrosion prognosis, loss prognosis. We will develop novelty detection methods as well to assess more efficiently the remaining useful life of the structure at wind farm level. And here we will develop a platform to collect and to gather all the data coming from work package 2 and integrate also data coming from other deployed sensors, IoT sensors currently deployed. Okay. And finally, in work package 4, we will work on wind farm control strategies to get smart power dispatch in curtailed conditions and to optimize the operational maintenance scheduling. Here, the main objective is to design a smart tool to facilitate this work to the operator, okay, to the offshore operator. Okay, then WILLOW will work on mainly on 2 use cases. It's difficult, all of us know that it's difficult to get data coming from real infrastructures to get our models more reliable. And in WILLOW, we pretend to minimize this barrier thanks to the data coming from our operator, Northern. Then this is one of the use cases, the Belgian North Sea, where Northern operates an offshore wind farm with 44 wind turbines. And additionally, ENVV will participate in the advisory board of WILLOW. And that's why we have a second use case here in the Baltic Sea, where they operate a wind farm of 21 wind turbines. Then these use cases are different and complementary. In the first one, we want to analyze in depth the curtailed conditions and analyze how these conditions affect the fatigue life of the structures. And in the second one, we will apply wind farm control and novel inspection techniques. The idea is to get data from these wind turbines and to perform drone inspections as well. Apart from the data coming from real offshore wind farm, which is key, The idea is to use in the scope of WILLOW some test sites to validate our own developments, our own sensors and models. And yeah, these are two of them we will use: the Blue Accelerator in Belgium and the Hash Lab in the Basque Country. And we are now defining which kind of experiments we want to perform to validate the sensors, not only the robustness, also the functionality in real environments, and even to get more data for our models. Okay, here you can see some important outcomes of the WILLOW project. The first one is to provide open source data-driven tools with the aim of decreasing energy costs on operation, increasing total wind farm output, and to be able to evaluate the operational risks. The development of digital and physical tools is really important to get interoperable frameworks and controls, and be able to enhance data collection, analysis, and operation. To get better informed decisions on different aspects, farm-wide system optimization, lifetime extension, decommissioning, and of course to reduce the LCOE, increasing the remaining useful lifetime of these substructures. And the expected impacts of WILLOW regarding different kind of costs. The first one related to maintenance costs. Let's say that corrosion cost represents around 18% of maintenance cost. Then WILLOW pretend to reduce 50% of the inspections cost. With the solution we want to develop. In terms of design and operating life, WILLOW expect to provide 5 additional years of operating life. So let's say 20% of lifetime extension in wind farms which were designed for 25 years of lifetime. We expect to reduce as well the noise pollution by 4%. And in terms of LCOE, the aim is to reduce up to 10% of these costs of energy. Okay, and that's all from my side. Thank you very much for your attention. And if you have questions, I'm here.
Thank you so much, Ainhoa. It's really nice to see WILLOW again. So any questions in the group? Is it any?
Yes, hello. Thank you, Ainhoa, for the presentation. I was wondering which is the way you are considering wind farm control, if it deals with farm flow control or any other aspects in the operation of the wind farm. Thank you.
Thank you. Okay, in terms of wind farm control, the expert is SINTEF, okay. But the idea is to develop not advanced control algorithms. Okay, it's just to try to join the component degradation and or considering the component degradation, the most critical components degradation in this kind of control to get a smart power dispatch. That's the aim of the project. I don't know if I answered your question.
Yes.
Okay, but
thank you.
that's the aim.
Thank you so much.
You're welcome.
Any other questions? Well, I do have a follow-up question. I know based on Irene's question and then your answer. For the damage recognition in particular, sometimes the time it takes is really long, and WILLOW is only a 3-year project. Do you see that as a challenge? Do you have a plan to work on already damaged turbines, perhaps to fasten up the process? How do you approach to this?
Yeah, you're right. The corrosion, in fact, is a slow process. Then the idea is to produce some, regarding pitting, for example, to produce pitted samples to analyze the degradation in the laboratory, and afterwards to deploy those samples in the test sites, for example, in the HARS lab, and see how this pit grows, and to be able to monitor and quantify the pit and the progression of the pit, for example. Okay, so we need to produce our own damages in some way.
Yeah, makes sense. Any other questions? If not, I have one more, and that's about the sort of share of data, which is probably going to be a question for all the projects that is presenting today. So how much of your campaigns, how much of the newly produced data within WILLOW will be open to us all?
Okay, yeah, that's a key question, and very important. Then we aim to produce some part of our data available for everybody, okay? And we are talking about this intensively in our consortium to do that. The most of the models will be open source, all of them probably, okay? And part of the data will be public as well. But it's true that probably not all the data, but part of them to test the models and so on will be public.
It is a task in itself, isn't it, to define which data we can open and which data?
Yeah. Important task.
That is true. That is true. Thanks a lot, Ainhoa, for joining, and thanks a lot for talking us through WILLOW. Thank you so much.
Thank you.
And now we can continue with the next one, as I see no other questions to Ainhoa. In any case, you'll be around, so perhaps you can type it in chat if you come up with a question later on, and you can take it from there, Ainhoa. So the second presenter will be Jan-Willem, and he will talk about SUDOCO.
Very good. So can you see my slides? And can you hear me?
Yes, we have it. Yes.
Really good. So my presentation is also going to be a little bit shorter than anticipated, I would say. I have in total 4 slides, just the pictures from the proposal. So I have the honor to present the SUDOCO project, which stands for Sustainable, Resilient, Data-Enabled Offshore Wind Farm and Control Co-Design. So that's a long word, right? But it's a big puzzle, so that's why it's called SUDOCO. So it's data-driven, wind farm control, focused on flow control, and we also have a big part on control co-design. So what is the first slide that I would like to show? I muted myself. No, I didn't. Is this one. So this is the overall concept. As you might know, there are many wind farm control projects going on or ended. And the idea of this project is to integrate everything what's out there. Everything what's out there, if you, for instance, think about flow control, there are many techniques like induction control, wake steering, and nowadays people are also interested in more dynamic actuation techniques. Think about the helix and the pulse. But you can also imagine that you don't want to run these algorithms full time, right? You only want to, maybe with partial overlap, you want to do wake steering, and with full overlap, you want to do some kind of dynamic induction control or induction control if you also take loads into account. So how you should see this is that we're going to explore hybrid solutions and which control technique do you want to use and for which condition do you want to use it. Then you also, if you look at the block next to it, you also can play with your controller if you want to make it aggressive, if you look at the energy yield, or you want to make sure that hey, maybe my energy yield is not the most important thing. I think loads are more important, that you really can find the optimal on your Pareto curve. I will come back to a Pareto curve in a minute. But also, for instance, that you can say, okay, my wind farm should at least deliver this amount of energy as some kind of base load. Then, of course, all these things are related to what is your objective, right? So you can think about euros as an objective, but you can also think about the environment as an objective, or a mixture of all these kind of things. So you can think about multiple objectives, and we're also going to explore different objectives in this project. Then if you look at the left-hand side, I think that's another important thing about this project is also for wind farm control, flow control, we try to make it as realistic as possible. So what we try to do is also work with time varying flow conditions, environmental conditions, such as wind speed, wind direction, and you name it. But also sea conditions, for example. And the other thing which is important but not listed here, we're also going to look at large wind farms. So not only at toy problems, but also at wind farms with at least 50 turbines in there. Then the other element at the left-hand side is also the time-varying market conditions. So you can think about with low wind speeds, you get more euros for a kilowatt hour. So maybe you want to be more aggressive in producing energy. If there is a lot of solar available or the higher wind speeds, then maybe you also want to change your target a little bit. Now, then, of course, we also look at loads and O&M and all these type of things. So that's what we try to integrate in the so-called control room of the future. So what it also entails is at some point later in the project, we're also going to add storage devices, also a little bit of solar power, and you name it. So that is what we're trying to build. We try to build a control room of the future where we look at different objective functions and different flow control technologies. So what is then the outputs? You get different time varying outputs. That's what you see at the right-hand side, but also help. And the other thing that I didn't mention yet, which is also essential, it was also essential in the call, is that we have to look into security of energy delivery. So that's of course that your health of the wind farm of your asset is okay, right? The health monitoring aspect, but also what's in this project is a little bit of cybersecurity to make sure that our asset is protected against cyber attack. So that's also a big thing within SUDOCO. So that's also where resilient is coming from if you look at the title of the project. So what you see here is basically in a nutshell the main concept of the SUDOCO project, which will run for 4 years, and it started in October this year. So if you now look at the structure, but before we go to structure, I have to explain a little bit what I mean with the Pareto curve. So a Pareto curve is really, hey, how aggressive do you want to be? So in this example, at the left-hand side, you see, for instance, the yield with a minus sign in front, right? So that should be as low as possible then in this case, and loads should also be as low as possible. So with nominal operation, we envision that you're on the green line, and you want to create this type of trade-off curves as function of the different flow control techniques that we have, right? And if you have this, then you can play where you want to be on this curve, but there are also, of course, barriers if you look at loads or whatever, the health status of your turbine. So that's let's call it yellow, the yellow blocks here, and that's point B. Now, then you also want to play around, and depending on the objective function, you are somewhere on this curve. And in this case, it's two-dimensional, but you can imagine that there are many dimensions which you can add to this Pareto curve. But this is the most simple one to explain. Now, another important element of the project is co-design. So at the moment, we have flow control. You can also think about, hey, let's change the park layout, or how you operate your wind turbine, or complete integration with storage, and you name it. And that means that you maybe can really change your Pareto curve. So what we hope to do with co-design is that this Pareto curve will move further to the bottom left, right? So it basically means more energy and then with lower loads. That's what we try to achieve with co-design. And of course, the easiest one to explain is with the park layout. So if you have now flow control technologies, maybe you can reposition your turbines a little bit more, you can increase the energy density, or you can play a little bit more with loads. So that's also part of this project. Then if I continue, so we have in total 8 work packages. Of course, we have input from old projects like Meridional, CO Windcon, which is an old wind farm control project, Farm Connors, Total Control, also an old EU project. That is the input for SUDOCO. And of course, we also try to align our efforts with the other EU projects granted in this round, such as TWAIN. So what the work package that we have flow control. So how to control the flow. I talked about induction control, wake steering, and you name it. So we are in the lead there, the TU Delft. Then we look at, in work package 2, at loads and health monitoring. And yeah, modeling that for wind farm. So there TWAIN is in the lead. Then we have a dedicated work package in looking at different value functions, so the objective functions, and that is where DTU is in the lead. And all these 3 elements, loads, flow models, and then the value functions, are then part of the control room of the future, where Wind Renewables, a company from Spain, is leading the development of the control room of the future. So that is basically the core also of the project. Now, what you then see more at the right-hand side, the work package 6 and 5. So 5 is the co-design aspect. So suppose that we have this framework, can we now play with the positions of the turbines and you name it, and then using the control room of the future. So that's also led by DTU. And then we have work package 6, where we are basically going to define some use cases of the different technologies that we will develop. So it's the combination of flow control techniques, it's a little bit of co-design, it's a little bit of cybersecurity, also model validation with real data from an offshore wind farm, and also the system integration part. And of course, there we also are going to use the control room of the future. What I forgot to mention there is that we also are going to do wind tunnel tests in Milan. That's also important. Now then we have the classical work packages, work package 7 and 8, dissemination and exploitation, and the project management. So work package 7 is led by ICANS, and we are responsible also for the project management. So I already mentioned that we're also doing wind tunnel experiments in Milan. So that also means that the Politecnico is a project partner. And we also have a little bit of floating in the whole scope of the project. So how all these techniques translate to floating wind farms. And that's why we also have Sowento, a small SME on board, or reasonable sized SME on board. So that's more or less how the project is structured. We have not 4, but 5 parties in the advisory board. So that's Windesco, which are developing wind farm control technologies. We have NREL, of course, for the flow control techniques. We have Crosswind. Crosswind is a joint venture of Xiaowei and NACO, and they're developing a wind farm in the Netherlands, where we also will get data from. And they are using Siemens Gamesa turbines. So Siemens Gamesa is also one of the partners in the advisory board. And last but not least, we also have a company that has experience with cybersecurity, especially for offshore wind farms, and that's Applied Risk. So in total, we have 8 partners working on the project, and we have 5 partners in the advisory board. So that's in a nutshell the SUDOCO project. As already stated, we started in October, and we're slowly trying to start up the project. So no first results or whatever. Hopefully in a couple of months from now, we will have the first results. Thank you for your attention.
Thanks a lot, Jan-Willem. All right, any questions from the group? Maybe while they're raising their hands, I can ask 1 or 2. So you have mentioned co-design being one of the most important things, but it's also a data-driven project. So how do you approach to the challenge of data not existing for the new farms coming in? Do you then sort of patch it up with numerical simulations, or how do you approach to that?
An excellent question. So my first answer would be they are decoupled from each other. Partly decoupled, right? Because we also use data to train our models, right? So we train our models using data, so you can already call that data-driven control. So it's not fully data-driven. So in the field of data-driven control, you can say, okay, we only use data for decision-making, but you can also say data-driven control is where you use data to upgrade your models. So if you have better models, then again, you can use these models for co-design. So if you look at SUDOCO, then we use the data to develop better models, especially for dynamic events.
So it's adapting, right? If it's
Yes.
for the purely data-driven models, it's a bit of a limitation for data that is not seen before. But if you're doing maybe more data informed, then it gives you flexibility. All right.
Absolutely. Yeah.
All right. So perhaps I can also repeat the question I asked to Ainhoa regarding the availability of data and the data share coming out of SUDOCO.
Yeah, so we are using quite some open data sets, which are already out there. We also will generate a new data set, and that's a data set we cannot share. So that one is only for a couple of partners. So then I'm talking about the data coming from Hollandse Kust Noord, where we will do some dedicated wake steering experiments.
Right. Any other questions from the group? If not, thanks a lot, Jan-Willem, for your time and showing us what SUDOCO is like. And we can continue to Iconic now with Xiaowei.
Okay. I try to share my screen. Can you see my screen now?
Have it, yes.
Okay. Thank you very much for the invitation. Good afternoon, everyone. I'm Xiaowei Zhao from University of Warwick. Today I will give an overview of the Iconic project, which represent smart, aware, integrated wind farm control interacting with digital twins. I was the project coordinator of the Iconic proposal. As the UK was not associated to Horizon Europe in the summer, I transferred the project coordinator to Ghent University. Then the UK part is funded by Innovate UK. I'm now the scientific coordinator, responsible for the scientific coordination of Iconic. I also lead the communication, dissemination, and the exploitation. Ghent University performs the non-scientific coordination, so it's a joint lead. the good news is the UK will join Horizon Europe in 3 weeks, so we will not have this issue in future projects. The Iconic project kick off at the beginning of this month, and it will last for the next 4 years. The Iconic project has 14 partners, including 7 academic partners, 7 industry partners across 7 countries. In this project, Warwick works on intelligent farm-level control, farm-level digital twin, machine learning-based wind farm modeling, and aero-hydro-servo-elastic modeling of the 20 megawatts wind turbines and their controls. Ghent University focuses on turbine control, tackle economic optimization, as well as wind farm LCOE analysis. NTNU works on wind turbine digital twin. Alba works on turbine level control, ancillary service, and cybersecurity. Imperial will mainly focus on wind tunnel experiments and the validation of the digital twin and the control. KU Leuven and Eclan work on modeling and digital twin of key turbine components, including main bearing, pitch bearing, gearbox, and generator. Regarding the industry partners, Sea Power is an offshore wind farm operator, works on validation of control and digital twin using the operation data and field tests. EDR, SKF, Lowlagen, and ZF work on digital twin and their validations at the components level. As I mentioned earlier, this including the generator, bearing, and the gearbox. BP works on wind farm control and a case study based on one of their onshore wind farms. So we focus on, we cover both onshore wind farm and offshore wind farm. Ambotech supports the control, solution design, and deployment. So it's clear that Iconic covers the farm, turbine, and components level, allowing us to develop control and digital twin across the system hierarchy. The overall ambition of the Iconic is to develop an integrated wind farm control system to improve the whole farm's operation efficiency, thus leading to more stable, resilient, secure, and reliable wind power. The Iconic control system will be AI-based, data-powered, and physically informed, consisting of farm, turbine, and components level. The integrated control system will be further supported by the cutting-edge simulation tools and digital twins that will be developed within the Iconic to enhance the control performance. Iconic will then further explore the AI-powered life management and the cost reduction. Finally, a core feature of Iconic is a comprehensive validation of the control and the digital twin innovations via simulation, historical data, wind tunnel test rig experiment, and the real-world field tests. To deliver this ambition, Iconic has 4 objectives. The first objective is to improve the farm-wide operation while developing AI-based wind farm control tools. The second objective is to deliver farm-level objectives while developing turbine-level control solutions. Objective 3 is to enhance the performance of the Objective 1 and Objective 2 by developing digital twin and physical tools as a control enhancer. And this enhancer will improve the awareness and the control performance with consideration of the remaining useful life assessment of the key turbine components. Objective 4 brings together most of the innovations and to TRL file through this comprehensive validation and tests, as I mentioned earlier. So based on these 4 objectives, Arconic has 4 technical work packages. Work package 2 is about farm level control. Work package 3 is about turbine level control. Objective 4 is about the development of the digital twin. Work package 4. Work package 5 is about the comprehensive validations. Also in work package 5, Warwick will put everything together to form a open source toolchain for wind farm control systems. In addition to these 4 technical work packages, we also have the 2 management and dissemination work packages. So here is an overview of the main modules, Arconic innovations and their connections. The farm level control will be developed based on the deep reinforcement learning approaches, which will including fatigue distribution and impact minimizations, as well as cybersecurity design. So it will provide control reference for turbine level control. The turbine level control will cover torque, pitch, and yaw control with consideration of fault-tolerant mechanisms. All this will form the first version of integrated wind farm control system. Then the digital twin will be developed. The farm level digital twin will be developed to predict the whole flow field information. Then turbine level digital twin will be developed with the consideration of the load and fatigue distribution of the key turbine components. They will be integrated together to support the control. All this will form the second version of the control system, which is a digital twin enabled AI-powered control system. Both the digital twin and the control development will be supported by the modeling tools that will be developed within Arconic. They including both physical based model and AI-based models. The models, digital twin, and the control system will be comprehensively validated and tested via simulation, operation data, internal test rig experiment, and field tests, as I mentioned earlier. Finally, the lifetime management and the LCOE justification studies will be carried out to maximize the benefit of the Arconic innovations. Next, I will go through 8 main research highlights of Arconic. The first research highlight is AI-based control-oriented modeling of wind farm wicks. As we know, safety models which can accurately capture the wind turbine wick interactions is computationally expensive. While on the other hand, the analytical wick model, which can be evaluated in real time, cannot capture the detailed flow feature. In Arconic, we will develop AI-based wick models which can achieve prediction of high-fidelity flow features. Similarly as a safety model, while can be evaluated in real time, similarly as an analytical model. The overall framework is to first generate a CFD database capturing the high-fidelity flow dynamics. Then a novel machine learning structure will be designed and trained based on such dataset. After training, the machine learning model will be used for control design. The second research highlight is the farm level control. Here we, as mentioned earlier, we will develop this based on deep reinforcement learning. So in addition to what I introduced earlier, we also consider automatic grouping strategy for large wind farms and a novel actor-critic distractor network for enhanced robustness. Furthermore, a mechanism to enhance the cybersecurity will be developed. The third research highlight is turbine level control. Here we are going to develop a new MPC approach in order to improve the performance of the control system and ensure strict safety requirement. The use of the ladder preview will also be considered here. So all these proposed MPC methods for wind turbine control will benefit from Embotech's Forces Pro Suite, which is a commercial product for deploying MPC and the numerical optimization in wind turbines. This will help accelerate the deployment of the iconic control solutions to the real world. The fourth research highlight is farm-level digital twin, which will be developed via physics-informed deep learning approach. The digital twin will be developed to provide full awareness of real-time wind flow covering the entire wind farm. This will be achieved by fusing various data and physics simultaneously into physics-informed neural network structure. By physics and data fusion, the digital twin will provide wind flow field information that cannot be directly measured by current sensor technologies, nor predicted by conventional machine learning approaches. Here we use physics-informed machine learning to achieve to get all this information. With this rich flow field information, the farm-level digital twin will be combined with the turbine-level digital twin to provide digital mirroring of the turbine structure in real-world operating scenarios. The digital twin will then be used to support the wind farm control system, and it will finally be integrated into Iconic's second version of control system, which is digital twin-enabled AI-powered wind farm control. The fifth research highlight is the turbine-level digital twin, including key turbine components. This including the drivetrain, the generator, the main pitch, and yaw bearing. Here we have the industry partners, which covers which are the suppliers of these components. The high fidelity model of these critical components will be developed and calibrated with historical data. Then surrogate models to achieve real-time performance will be built either by data-based machine learning approach or hybrid approach, depending on the components' characteristics. So this surrogate model will be integrated all together to form the digital replica of the physical system. Such a digital twin system, along with the online sensor measurement, will then be used to support the control and management, considering remaining useful life of the key turbine components. The next research highlight is the setup of these 3 case studies that cover an onshore case, an offshore case, and a future wind farm case, considering 20 megawatts wind turbines. The offshore case study will be set up according to Sea Power's wind farm. The onshore case study will be set up according to one of the BP's onshore wind farms. And a virtual wind farm design will be set up in the North Sea with the reference 20 megawatts wind turbines. So we will develop this wind turbine model in this Iconic project. All these 3 case studies will be used for the evaluation of the digital twin and the control systems within simulation environment. It will ensure that the iconic innovations are generic to wind farm and turbine specifications, therefore maximizing iconic's potential impact. The 7th research highlight is the extension and adaptation of the developed control and the digital innovation towards the future 20 megawatts wind turbines. A prototype 20 megawatts wind turbine model will be designed. The aero-hydro servo-elastic modeling and control of these 20 megawatts wind turbines will be developed. As one of the major difference of such wind turbines compared to the existing turbine lies in the strong aeroelastic effects. Finally, a virtual wind farm consisting of these future 20 megawatts wind turbines will be set up in a simulation environment. It will be used for exploring the control and digital performance for such future wind farms. We will also develop a repowering strategy using 20 megawatts wind turbine for sea-powered wind farm to demonstrate the use of the tools developed within Iconic for repowering and decommissioning scenarios. The last research highlight is the comprehensive validation, as I mentioned earlier. This including validation by simulation, historical data, test rig, wind tunnel experiments, and field tests. At wind farm level, numerical tests will be first carried out via large ID simulations at atmospheric boundary layer and wind farms. Then validation by physical experiment will take place at a very large low-speed wind tunnel at Imperial College. Extensive turbine array experiment in realistic atmospheric simulation will be carried out, where spatial extended high-resolution measurement will be achieved by a combination of PIV and point velocity measurement. Such experiments are enabled by the long test section of Imperial College's wind tunnel, which is one of the longest test sections in Europe. At the components level, the test bench for critical components will be available at Lowlagen. Finally, the field test will be carried out in Sea-Power's wind farm, which has 54 5 megawatts and 6 megawatts wind turbines. There we are going to install LiDAR system to test the digital twin and the wind farm control system. With all these tests, we expect the Iconic innovation are very validated before the end of the project. And we hope the major innovation will reach TRL5 at the end of the project. Finally, Warwick will put everything together to form, as I said earlier, to form an open source toolchain for wind farm control system, and we will share with the community. And thanks a lot for your attention. This is a quick overview from me.
Thanks a lot, Xiaowei. Iconic is really ambitious project. Any questions from the group? But I'll try to keep it short. So the very first one is, this is something we always discuss also with my colleagues. How do you define digital twin?
Digital twin is a dynamic mapping of a physical system. Through
modeling, right? Any kind of model.
Yes, here is through the AI modeling here. There's a sensor information connects between the physical twin and the digital twin. Here we did a bit further. Basically, we use the information from the digital twin, then we feed back to the real world control system to affect the physical twin.
Okay, that's pretty cool. So
Yeah.
second question about the digital twin of a turbine itself. Do you, maybe I missed it, but do you have any turbine manufacturers on board for really detailed information, or you want to keep it sort of generic?
We don't have a turbine manufacturer, but we have a wind farm operators, Sea Power. So and then we have Ambotech, which is a software developer for OEMs. And we have components manufacturers of wind turbines. So, yeah.
Okay. So it's more the digital twin of a response of a turbine per se, right? Maybe it's not full components, and maybe it's not the blades at least.
Because there's already a project for the digital twin of blades, so we didn't do this in accordance. So we do at the farm level. We focus on flow system, and in the turbine level, we focus on the main components.
And you mentioned one more thing about the digital twin for the 20 megawatt turbine. So I was wondering if you want to maybe connect with the colleagues in the other IEA tasks. So that's task, I think, now 55. It is reference turbines and reference wind farms. So they are now working on IEA 22 megawatt turbine. I think it's going to be released officially by the end of this year. Yeah, it might be a digital twin also the way you define it. So perhaps it might be a good way to connect.
Yes, I got email from them. I think it's super relevant. So yeah, I'm looking forward to see their models.
Yeah, of course. All right. Any other questions? If not, thanks a lot, Xiaowei, for your time and for your talk. Thanks a lot walking us through Iconic.
Thank you for the invitation.
All right. So I guess it's my turn now. Let me find the slides. Now I will talk a little bit about TWAIN, right after I manage to share my screen. I hope you can see it well. Irina, I see your hand is up.
No.
Oh, wasn't it? Okay, so maybe it's this one before himself. All right, so we can then start with TWAIN. TWAIN is the last project we're presenting today, and it's the acronym is a little complicated. Originally, we thought we should start with TWARS, Integrated Value-Based and Multi-Objective Wind Farm Control, powered by AI. But then towards the end, close to submission, we thought maybe TWARS is not ambitious enough. So we sort of dropped the TWARS. Then TWAIN became without T, but still. TWAIN as an acronym works very nice, and it's also a little bit sort of saying hi, a little nodding to Mark Twain, who is also a great author. So that's why the acronym sort of stayed. So we are looking at, as all the other projects presented today, an integrated wind farm control. Definitely have quite a bit of flow control in it. But what we're trying to achieve with TWAIN is sort of take things a bit further and perhaps come with a more comprehensive, quantifiable to a certain extent definition of value, as well as a big focus, high focus on multi-objectivity, particularly because we're looking at a lot of interesting onshore challenges that wind farm control can be relevant. All right, so this is our little, in a nutshell, picture. So you can see in the green part on the figure, that's more representing the business as usual. You can see how the wakes look like. You can see what happens to turbines when there are birds and bats around, which is typically a shutdown. And you can also see there is no wake behind the turbine that is shut down. And then there are typically houses nearby, some residential areas or forests, etc. And then within the TWAIN, one of the things we want to achieve is a bit like digital twinning, perhaps, as the way Xiaowei describes it. But it's basically to try and come up with a mapping, sort of digitalization of the system going on, and that we think is quite crucial to be able to establish, facilitate the communication between all these processes that is affecting a wind farm operation. Because the turbines interact with each other, that is something perhaps we've been covering a lot, especially under this task, farm flow control. We're looking at the turbine-turbine interactions, sometimes farm-farm interactions. But one of the things we want to look at in TWAIN is how the turbines also interact with a wider environment. So what happens normally nowadays is when the turbines need to communicate with each other, it happens through typically greedy controllers within a given wind farm. And then, of course, taking this aerodynamic interactions into account is already a step ahead, which we assume where we are at right now. That's the industrial baseline, let's say. But digitalization of all the processes that is affecting is quite interesting for us. That is looking a little bit more towards the holistic operation management, as well as a sort of a better, more smart, more intelligent support in decision making, and the integration at the design phase potentially for the bigger wind farms coming up, and maybe also operating under relatively different weather conditions with climate change, etc. So perhaps more interestingly than the others, some of the things we are ambitious enough to do is to take a little bit of social aspects into account. And that is, some of it is quantifiable through noise or sound, or the disturbing or annoying version of sound, which is noise. So as we know, the turbines do emit noise, and then they're also propagated given the terrain, given how far the residents live, etc. Of course, the mitigation of such noise for higher acceptability is of interest, and of course, affordability of green electricity by increasing potentially the power of the existing wind farms should also contribute to acceptability. But how does it come together? What happens when you downregulate a turbine, either through axial induction or through wake steering? What happens to the noise then? Is a bit of a research question still. And then after you employ sort of a noise curtailment on a turbine, how does it affect the wake? How does it affect the overall operation within a wind farm scale? Is a nice research question. Then, of course, we have the wildlife. That's another process, let's say, or a phenomena that affects the operation of wind farms. And that will be the birds and bats typically around the turbines. It's not exclusively an onshore problem. It's happening also on offshore, quite a bit, I heard, depending, of course, where you are in the world. The way to sort of avoid any kind of collusion, any kind of direct interaction is to curtail or interrupt the operation entirely of the turbine or the wind farms. But of course, how does it affect the revenue stream, or how does it affect the optimal operation, the control settings that you come up with, is another interesting question. One of the things I learned working with TWAIN was there's actually OEMs, and Icon to be precise, they are selling bad forecasts in the German market on a daily basis, because it is actually essential to sort of identify the prices or how much you want to bet the next day, because you might actually have to turn off all your turbines or curtail to a large extent. One of the last things, let's say, that we're considering that might also be a little different from the earlier talks is the precipitation and rain. So as we know, or as you might know, the precipitation and rain in particular in this part of Europe are the main drivers of the leading edge erosion. And they're also the sort of the most costly and the sort of the most troublesome part of the unscheduled repairs. And they are really adding to the O&M costs onshore, but also definitely offshore. Currently, they are mitigated through torque control. That is actually referred to as erosion safe mode. But how a single turbine level erosion safe mode is generalizing towards a farm level, and then perhaps a series of wind farms clusters or asset level, is something we would like to include in our value chain. All right, so this is our methodology in TWAIN. We refer them as pillars. So those pillars reflect the objectives of the project. They also reflect the work packages of the projects. They also reflect the toolbox of the project. So as the AI, which is very highlighted in TWAIN, it is quite a bit of data-driven project. And we're also quite sort of ambitious in the way that we want to do, let's say, IT this time, and a bit more software engineering, perhaps more and more included to our daily work. So in that regard, we are actually starting with the very first pillar, which is the foundational pillar as well for all the other pillars. That's also our first work package, and that's the data management. And the first one is the data management toolbox. So that's the one that's collecting the data. That's the one that is ensuring safe, share, and selective access towards best practices in data tenancy, etc., among the consortium and also the users at the end of the project. And then it's also responsible for the creating the environment itself, which is going to be the decision support environment for wind power asset management. And that's a sort of secure by design environment, or the structure is built also in work package 1. Then work package 2 sort of feeds into that, and that is about integrating the wind farm control processes. So that is the toolbox that is looking at the wind farm operation overall. That is the one that is digitalizing all these processes we talked about. So that would include the wind farm response. That's a little bit business as usual, if you will. So that would model the power of the turbines, structural load response of the turbines, etc. Then we would also add failure and damage models on that, as well as the insurance, the grid compliance, and maybe potentially adding additional services. For example, let's see how the synergies with newer services will work. For example, Black Start and grid farming. And then, of course, we also have the eco-social consciousness. So the more wildlife and social aspects related digitalization tools or toolboxes will also go under work package 2 there, or the pillar 2. Then we have pillar 3, where all these processes became a bit more value-based. So this is where we define the metrics, the performance metrics, and we integrate them. Of course, a majority of them are economic metrics. So that is the revenue streams. That is the definition of income and outcome for a given site at a given time. Of course, there is also the societal and environmental metrics. Some of them are direct performance indices, like maximizing, minimizing, or some of them are actually constraints, for example, noise coming into the rest of the control framework. Then we also have the definition of risk and uncertainties defined under work package 3 there, and we define some safety control tests and failure tests, etc., for the actual risk. And then we also have some uncertainty analysis and how it fits back to the controller. The controller itself, though, is coming in work package 4 or pillar 4. And that is where we are integrating multi-level controllers. That's a little bit similar to the exercises we've been doing in farm corners, if you were following. So that's going from turbine controller to farm flow control to the power plant control level, which in total I refer to as wind farm control now. And then that pillar or the work package looks also at the optimization. So that's the optimized design and the optimized operation, of course. That is also the place where it provides decision support or a series of decisions for humans to choose from. And then we have the main environment testing and validation happening in pillar 4 with a small field testing, which I'll talk about a little bit. So then our last work package, which is the last pillar, is the integrating wider audience to the TWAIN environment overall. And that is to come up with the innovative communication, dissemination, and exploitation solutions. It's perhaps a little different than the classical CDE as well, because this time we're actually defining an open call. So we are releasing version 0 of the TWAIN 1 year before the project ends. That means 3 years from now. So we're releasing it then, and then we're opening a call for particularly software companies, AI-based companies, to try and give us the sort of external user feedback, so what they refer to as UX, so that we can actually have time to improve our version 0. And by the end of the project, we release version 1, which is already tested by at least some of the stakeholders. All right. So our overall aim is to support the wind farm owners, operators, of course, to make better decisions for their system-wise optimized performance. System-wise optimized, but still very much case and site specific. So our concept in TWAIN pivots on these 5 pillars, as we said, and that is about the full integration of wind farm control. So the first one would look at the integration of multi-source and multi-format data. That would be the power data together with load data, together with bird monitoring data, together with noise data. So really different textures and formats of data, as well as different lengths and from different parts of the world. Number 2 would be the AI-enabled integration of multidisciplinary processes and phenomena affecting the wind farm operation. This is where we think the AI is actually shining for us, because then having all these different kind of textures and data set, if we manage to have at least data-informed modeling for many of this, we believe the integration of the models or the communication between the models, different scales, different inputs and outputs can actually be harmonized. This is where we plan to leverage a lot of the AI-based specs, let's say, of modeling. And then 3 or pillar 3 would be the integration of multi-objective prospects. So that will be the benefits, that will be the constraints, that will be the overall performance metrics for any kind of wind farm control action, so that we can assess the true added value of a certain operation mode. And then the fourth one would be, of course, the integration of multi-level controllers then, and scenario analysis, which I will also present what the case studies are in a bit. And our idea is to support the owners operators for that, to provide this decision support for harmonious coexistence, which we believe is going to be more and more important in the future, since the targets of onshore, increase in onshore wind farms is also quite a bit of a popular thing nowadays, as well as offshore. All right, and then the last one would, of course, be the integration of wider audience to TWAIN outcomes, so that we make sure that people actually do use it by the end of the project. Yes, here is some of the outcome and interactions among the toolboxes. So let's start from left. Don't let it confuse you. It's a bit crowded. Of course, we always have this page limitations in proposals, so we try to fit as much information as possible to each and every figure. So hence it's a little crowded, but I'll try to walk you through it. We start from the data management toolbox, as I mentioned earlier, and over there we have the social environmental data coming in, as well as the operational maintenance type of data. And data management toolbox gives us the data quality assessment, and it also gives us anonymization of the data where relevant for which wind farms that are relevant, because we do have direct competitors as partners in our consortium. It also gives us a standard way of labeling the data and also processing the data, as well as a secure architecture with AI/ML capabilities, so that we can put in our trained models on top of it later on. So these are fed into work package 2, or the toolbox 2, that will be wind farm operation modeling toolbox. And that is giving us the retrained, verified, and validated data-driven models. For example, modeling power loads, damage levels, failure modes, grid requisites, on-off, noise, and wildlife. Some of them are constraints, some of them are direct objectives or quantifiable objectives that will become more of a value base or wrapped up in more like a value base or KPI indexes in work package 3, and that's the socio-economic environmental assessment toolbox that is giving us the actual objectives and constraints. So that will be, for example, power to AEP or power to money, basically income, or O&M cost as outcome, and then the remaining useful lifetime, LCOE, etc. And then we have all of this objectives and constraints feeding into decision support toolbox, which gives us this series of optimum decisions for humans to choose from. And we also perform the field validation of some of the integrated wind farm control settings. It's a limited validation, not full, as we are looking at a very multi-objective approach. We only can do validation of some of it. As we mentioned earlier, the validation of extension of lifetime is not necessarily a 4-year project job. So all of them are wrapped up in a version 0 and then released in an open call for external end users. We're actually also paying for the external end users to use it and give us feedback. So all these toolboxes, all these work packages, let me tell you who does what. So the first data management toolbox is led by a software manager company that is called SoftServe. They're from Poland. And the second one, the wind farm operation modeling toolbox, that is led by TU Munich. And then the third one, socioeconomic and environmental impact assessment toolbox, that is led by us in DTU, and that's my colleague Nikolai, who's the work package lead in that. And then work package 4 is the decision support and the multi-level controllers, that is led by Senay. Irene in this call, she's the lead on that. And then our last one, open call for external end users, it is led by communication and open call AI incubator company called F6S from Ireland. In addition to this, we have, of course, additional partners, which I'll mention at the end of the presentation. Before we go there, let's talk a little bit about case studies, so where we want to showcase some of these things. So the first case study is focusing on evaluating the environmental and social ramifications of potential wind farm control actions. So over there, our objectives, which will be the same objectives for all the case studies, by the way, our objective is to reduce the LCOE and increase revenue. And this time we also have the social environmental one, trying to reduce or at least quantify and see the effects of carbon footprint. And then for risk and uncertainties, we're looking at increased security, stability, and reliability of electricity supply. And we, of course, want to reduce the integrated risk. The constraints are the main things that is sort of changing in between the case studies. Here in environmental and social ramifications case study, we do have the noise constraint and the wildlife constraint, particularly in France, we're looking. And then we would like to, of course, increase the resilience of the system or the controllers, that is finding solutions for those constraints, still trying to optimize or increase the objectives listed on the left. This will be applied to some of the NG wind farms in France, NG green wind farms in France. The second case study is to see how these algorithms can actually adapt to offshore. So this is a little bit to check also on the limitations of the AI machine learning algorithms, how they can go from one sort of particular domain to the next. As I said, the objectives are pretty much the same in all the case studies, but here the constraint is to see the adaptability and generalizability of AI, especially for large offshore wind farms, because it might not be necessarily very flow control oriented. The control settings that we find in the first case study, we want to see how they are scaling for the wake-based or more flow-based control settings in this adaptability to offshore case study. The third one would be to look at layout co-design with wind farm control. We have it just a little bit, not as much as SUDOCO for sure, also because we wanted to include 20 plus megawatt wind turbines. Purely onshore cases would not necessarily facilitate such big turbines, so we would like to see how the algorithms are actually looking into future, both in terms of turbine size and also in terms of the climate change. So we would like to run a couple of climate change scenarios, particularly for market analysis as well, so that market at 2050 and the weather is also simulated under climate change, particularly coming from WRF, etc., WRF simulations, etc., to see how we can actually design the wind farm under such market, under such weather, looking towards 2050 and beyond. And our last case study is looking at the end of life. So this is to try and come up with a series of decisions to help owner-operators to choose between extension and repowering, basically. For this, we will be looking particularly at the data coming from one of the NG, this time NG Global wind farms in Germany, and that is already more than 15 years old. So we will be looking at cases to see if the reduced use of land via closer spacing is meaningful, reduced visual impact potentially via repowering is actually a reality, or is it relevant for that site? And then we will again be looking at the resilience and if we can increase that. All right, there will be two campaigns in TWAIN. So the first one is the acoustic tests. This I don't think will be fully open, but the outcome from it can be open and can be of interest for the community. So here, NG Green, with support from us and NG Warwick, or Global NG, they will be performing a novel field campaign for acoustic measurements to see wind turbine noise emission and propagation potentially. So this is to see basically when we steer the turbines, what happens to noise. There is only one similar study to this by our NREL colleagues that has been looking at this problem so far, but now we also want to have one in Europe also to see if we can actually have this trend, the correlation, to see if we can actually reduce the noise via steering the turbines. And if we can we actually merge the objectives of noise reduction as well as maybe power neutral or power maximization, even still being under the noise constraints. And of course, we want to see how can we generalize the results or the observations coming from this campaign for other wind farms or other type of turbines, etc. The second campaign we'll be looking at in TWAIN is actually in Riso, where I work. So that's in D2 Riso campus. So you can see a little picture down there. So currently, if you've ever been to Riso, we have the big turbine. Let me see if you can see my cursor. Perhaps you can see my cursor right here. So we do have this big turbine already there that has a D2 logo on it. And then you can also see its neighbor. That's the second V27 we have. So this is a new V27. It's actually coming in a week. It's a nice little Christmas present for us in DTU. It will be very close to the road. So the next time you're traveling to DTU, this is the one that you will see the most close by. So looking at those two V27 turbines is monitored from everywhere possible is our exciting opportunity. It's an exciting opportunity for us in TWAIN. What we would like to do is to look at the power maximization with structural load constraints with a field test for the first time. And also we would like to see if we can have this income maximization with variable market scenarios. Because they are only two V27s and they're actually very close to each other. It's one of the smallest turbines in the world, of course. So, being in Denmark and all, we also refer to it as probably the smallest wind farm in the world. So it's very close to a Swift facility, but Swift has 3 turbines. So we are still smaller. This data set itself will be open. So once the turbine comes in connected, anyway, the data collected under it we will start publishing it maybe for other projects and other sort of studies as well. We also plan to use it for teaching extensively, etc. So you will be hearing about Riisa wind farm hopefully in the near future. And you can also see there is additional facilities coming in with some PV additions, and then there is also quite a bit of electrical facilities that are coming in. That makes our power system colleagues quite excited. So there will be some hybrid studies also for this Riisa wind farm and its neighbors. So I wanted to close by with the value proposition, what you want to sort of achieve at the end of the day with TWAIN, and what will be the main outcomes. So let's start from the value. So that's the blue in the middle. And then we have the analytics layer, and then we have sort of the data layer in gray. So the blue one is the value layer, and that would be the reduced risks, of course. Hopefully by the end of the project, at least we can showcase some of it. We want to increase resilience, increasing AEP, of course, decreasing structural loads, have some sort of gain in O&M costs, some sort of increase in revenue, hopefully some additional lifetime, reduced LCOE, reduced carbon footprint, and perhaps very interestingly, also having a look at the social environmental impact categories, coming up with categories for the first time so that people can use it for different kind of objectives and constraints for any kind of control problem or design problem. For the analytics layer in pink, we have of course, coming up the new models. So all the toolboxes I mentioned in TWAIN will be open source. It will be very nice to have a bigger community playing around with it. And of course, for the integration of the models themselves, and also integration of the sort of how to create metrics based on those models, which we think will be quite interesting. So all these interoperable toolboxes, as I said, will be open source. We will have the external user feedback with the open call itself. And then we will use, at the end of the day, more than 15 wind farms to create all our models and to field campaigns I mentioned. And of course, for the first time, we will have quite a bit of chance to work that closely and that intensively with a software company to come up with a secure by design data environment. So these are the exciting things for us. This is the consortium. I already mentioned our work package lead. So together with the ones mentioned, we also have TU Delft on board, of course. And from France, we have EDF and NG Green as competing operators, but still sharing data with us. So great success. We also have NG Warwick, which is a little bit more like the R&D sort of branch of NG. They're based in Belgium. And we have Rambo, both their Danish and their German offices. SoftServe is the software company I mentioned, and then F6S, I also mentioned the one from Ireland. Yeah, that's all I wanted to say today. So thanks a lot. Do you have any questions? Thank you, Lars. Okay, so if there are no questions, then yes, Darwin.
Yes, this is Torben. I can ask a question. I heard Jan-Willem talking about storage as well. And to be frank, I cannot remember what the caller said, but you are also kind of talking about wider perspectives, but are you also including storage? No.
Not in TWAIN, not in TWAIN. We said it's out of scope for us. We're not directly including it. But of course, it might be, depending on the site, it's simply because we don't have the data for it. So we decided to put the project around the data. So if we had the data, it would be perhaps interesting to look at how different revenue streams might be possible with storage also in the picture. But we don't have it currently.
No, yeah. I was just thinking it's really a huge difference if we have. I mean, we probably tend to think about wind farms and wind turbines, and there's some environment or some from outside that comes kind of a reference to what should the farm produce. But it really makes a huge difference if there's storage as well, and it has to be designed and controlled and stuff. Yeah. So I'm also a bit curious if I'm not sure if Jan-Willem is here still, but how much they will invest in that.
Yeah, I'm really not sure, but he left the call. So, but I'm guessing it's more on DTU's work package anyway, like he was showing. And from our end, it's Catherine Dykes who is heavily involved in SUDOCO. So So I'm guessing the facility that I showed you is also the facility some of those studies will be undertaken. So to be seen.
Okay, thank you.
Sorry, I don't know more to tell you more, Torben, but I'm sure we're going to hear more over time.
Yeah.
Any other questions? Right. So we have been recording the meeting. Let me actually stop that. We will put it up together with the